In the late 1980s, the Persian Gulf was a compressed battle space defined less by geography than by systems. Steel hulls, phased array radars, data buses, and human operators were bound together by an ideology of technological confidence. Warships operating in the region were no longer conceived as collections of independent sensors and weapons, but as integrated combat systems designed to collapse complexity into actionable certainty. The United States Navy's faith in this architecture reached its apex aboard the Ticonderoga-class cruiser USS Vincennes, a vessel whose defining feature was not its missiles or propulsion plant, but the Aegis Combat System embedded deep within its structural and electronic anatomy. Aegis was conceived during the Cold War as a response to saturation attacks by high-speed anti-ship missiles. Its design philosophy was rooted in redundancy, automation, and centralized data fusion. Multiple radar inputs, identification systems, and command functions were integrated into a single combat information center, where operators interfaced with the battle space through digital symbology rather than raw sensor data. The underlying assumption was that machines, properly designed, could manage volumes of information beyond unaided human cognition. Structural integrity in this context was not merely about hull strength or shock resistance, but about the integrity of information pathways, the uninterrupted, accurate transmission of data from sensor to operator to weapon. At the heart of Aegis was the /SPY, one radar, a fixed, phased array system capable of tracking hundreds of targets simultaneously. Unlike mechanically scanned radars, the SPY, one relied on electronic beam steering, eliminating moving parts and reducing material fatigue cycles associated with rotation and vibration. Its reliability was measured not in aerodynamic loading or thermal expansion, but in mean time between electronic failure and signal coherence under electromagnetic stress. The radar fed target tracks into a central computer, which correlated altitude, speed, heading, and identification data into a coherent tactical picture. In theory, this eliminated ambiguity. In practice, it transformed ambiguity into numerical confidence. Parallel to the radar architecture was the identification friend or foe system. IFF interrogators transmitted coded signals, expecting compliant transponders to respond with encrypted replies. Military aircraft carried Mode 2 and Mode 3 responses. Civilian airliners broadcast Mode 3 codes tied to air traffic control clearances. The system's design assumed correct mode selection, intact transponders, and unambiguous interpretation by operators. It did not account for cognitive fatigue, interface ambiguity, or the psychological compression of time during high-stress engagements. These were treated as human variables external to the system, rather than intrinsic failure points. Opposite this warship architecture stood a civilian aircraft whose own design philosophy was rooted in an entirely different illusion of safety. Iran Air Flight 655 was operated by an Airbus A300B2, a wide-body commercial transport engineered for predictable aerodynamic loading, pressurized comfort, and long-cycle structural fatigue management. Its airframe was designed around fail-safe principles. Load paths distributed across multiple frames, skins engineered to tolerate crack propagation, and systems redundancy intended to prevent single-point failure. Its navigation and transponder systems were optimized for integration into civilian air traffic control networks, not contested electromagnetic environments. The Airbus A300's Mode 3 transponder continuously broadcast a civilian identification code assigned for its scheduled flight from Bandar Abbas to Dubai. From an engineering standpoint, the aircraft was performing nominally. Its climb profile followed published departure procedures. Its engines operated within certified parameters, and its structural envelope remained well below design limits. There was no material failure, no fatigue-induced fracture, no aerodynamic anomaly. The aircraft's illusion of safety was based on procedural regularity, the assumption that adherence to civil aviation protocols ensured immunity from military engagement. The Persian Gulf in 1988 was an environment saturated with invisible stressors. Radio frequency congestion, overlapping military and civilian air corridors, and the constant presence of hostile surface contacts created a battle space where systems operated at the edge of their cognitive design limits. For the crew of the Vincennes, The day's operational tempo had already induced decision fatigue. Earlier surface engagements with Iranian gunboats had elevated threat perception, priming operators to interpret ambiguous data through a lens of hostility. In such conditions, system outputs were not evaluated neutrally, they were weighted by expectation. The Aegis Combat System displayed target tracks with alphanumeric labels, altitude readouts, and velocity vectors. These abstractions were intended to simplify reality, but they also obscured context. A civilian Airbus climbing along a commercial airway was reduced to a radar symbol whose behavior could be misinterpreted if correlated incorrectly. The system's confidence lay in its ability to present a single, unified picture. Its vulnerability lay in the assumption that this picture was inherently accurate. The concept of confidence in military system design is often treated as a byproduct of reliability engineering. Redundant circuits, hardened components, and rigorous testing regimes create a belief that failure is improbable. Yet confidence can itself become a structural load, exerting pressure on human decision-making. When a system rarely fails, operators are conditioned to trust it implicitly. Deviations are attributed to external threats rather than internal error. This is a form of cognitive material fatigue. Repeated cycles of correct operation reduce sensitivity to anomaly. In the case of Iran Air 655, the architecture of confidence extended beyond hardware. Rules of engagement, threat libraries, and training simulations all reinforced a narrative in which high-speed, descending tracks equated to hostile aircraft. The Vincennes combat system was optimized for detecting and engaging attacking fighters or missiles, not for nuanced discrimination between civilian and military profiles in congested airspace. The system could calculate closing speed and altitude change, but it could not assess intent. That interpretation remained human, yet heavily influenced by the machine's presentation. From a forensic perspective, the tragedy was not the result of a sudden catastrophic failure, but of a gradual alignment of assumptions. The radar did not physically malfunction. The transponder did not structurally fail. The missiles did not suffer guidance errors. The failure occurred at the interface between systems designed for certainty and an environment defined by ambiguity. The architecture of confidence collapsed inward, converting incomplete information into lethal decisiveness. This era of naval warfare marked a transition from analog caution to digital assurance. The Vincennes represented the future, a warship that could see farther, track more targets, and respond faster than any predecessor. Yet this acceleration compressed the time available for reflection. Decisions that once unfolded over minutes were now executed in seconds. The system's design philosophy prioritized reaction speed over deliberative verification, assuming that faster was inherently safer. In missile defense, this assumption held. In mixed civilian-military airspace, it proved catastrophic. The Airbus A300's destruction was instantaneous. The structural integrity of its airframe was overwhelmed by the proximity-fused warheads of surface-to-air missiles, which were engineered to shred aerodynamic surfaces and compromise load-bearing members. The resulting breakup was not a failure of aircraft design, but the predictable outcome of exposure to forces far exceeding certification limits. From an engineering standpoint, the aircraft did exactly what physics dictated when subjected to extreme external energy input. What failed was the invisible system that connected radar return to human judgment. The illusion of safety on both sides, military and civilian, was built on incompatible assumptions. One assumed that advanced sensors could unambiguously classify threats. The other assumed that adherence to civil procedures guaranteed protection. Between these assumptions lay a narrow margin where misinterpretation could propagate unchecked. This margin was eroded by stress, expectation, and technological faith. The Aegis system's designers did not anticipate a scenario in which a civilian airliner would be perceived as an attacking fighter, not because the data supported it, but because the context encouraged it. The system was structurally sound, electronically robust, and operationally effective within its design envelope. The tragedy occurred precisely because the envelope was exceeded, not by physical loads, but by cognitive and organizational ones. By the time the missiles left their launch rails, the outcome was already determined by a chain of subtle failures. No single component broke. No fatigue crack propagated. No material defect revealed itself under laboratory analysis. The failure was systemic, embedded in the very architecture that promised certainty. It was the cost of progress measured not in hardware losses, but in human lives, and it exposed a truth that would resonate throughout modern aviation and naval warfare: that the most dangerous failures are often those that occur when systems work exactly as designed. As the operational picture transitioned from static confidence to dynamic engagement, the environment imposed stresses that were neither visible on steel nor measurable in material strain gauges. The Persian Gulf on that morning functioned as a layered system of competing signals, where civilian air traffic management protocols overlapped with naval threat detection logic. This overlap created a zone of interpretive stress analogous to aerodynamic buffet at the edge of a flight envelope, not immediately destructive, but capable of inducing loss of control when exceeded. Iran Air Flight 655 departed Bandar Abbas Airport along a corridor that, on paper, was well defined. The flight path followed an established civilian airway, its climb profile constrained by air traffic control procedures and engine performance limits. The Airbus A300's aerodynamic loading during climb was modest, characterized by increasing lift coefficient at low airspeed and a gradual transition through flap retraction schedules. Structurally, the aircraft was in a low-stress regime. Pressurization differentials increased predictably, wing bending moments remained well within elastic limits, and no abnormal vibrations or control surface anomalies were recorded. From a purely aerospace engineering perspective, the aircraft was operating in an idealized state of mechanical normalcy. In contrast, the environment experienced by the Vincennes was one of escalating operational stress. Earlier surface engagements with Iranian patrol craft had already induced a heightened threat posture. Combat systems were operating continuously, radar arrays transmitting at full power, data processors cycling through high-density target tracks. While electronic components were designed to tolerate such loads, the human operators were subjected to cognitive fatigue cycles analogous to material fatigue. Repeated exposure to high-stress decision-making reduced margin for error, not through sudden collapse, but through gradual erosion of situational awareness. The /SPY. One radar illuminated the airspace above the Strait of Hormuz with relentless regularity. Each radar sweep generated returns that were filtered, correlated, and displayed as coherent tracks. Yet radar does not see aircraft as aircraft. It sees reflected energy. The interpretation of that energy depends on algorithms that assume stable correlations between altitude change, speed, and threat profiles. In congested airspace, where civilian aircraft climb slowly and military aircraft may maneuver aggressively, these correlations become probabilistic rather than deterministic. At the same time, the identification friend or foe system introduced its own layer of stress. Interrogation pulses and transponder replies were subject to timing windows, mode selection, and operator interpretation. A civilian Mode 3 response was present, but its significance depended on correct correlation with the radar track. In the Vincennes Combat Information Center, this correlation process was mediated through human-machine interfaces that compressed complex data into simplified symbology. Under stress, simplification can become distortion. Environmental factors further complicated the picture. Atmospheric conditions in the Gulf, including temperature gradients and humidity, affected radar propagation characteristics. While not severe enough to cause gross errors, these conditions introduced minor uncertainties in altitude estimation and signal strength. Such uncertainties are normally absorbed by system tolerances. However, when combined with human expectation of hostility, they can bias interpretation. A track climbing at a shallow rate might be perceived as descending if its data is momentarily misread or mislabeled, especially when attention is divided among multiple contacts. The Vincennes crew was operating under rules of engagement that emphasized self-defense against airborne threats. These rules were framed within a geopolitical context of ongoing conflict, where Iranian military aircraft had previously engaged U.S. forces. The psychological environment was therefore primed for threat confirmation rather than threat disconfirmation. In engineering terms, the system's feedback loop was biased toward positive identification of danger, reducing the threshold required to trigger a defensive response. This bias interacted with time pressure. Aegis was designed to reduce reaction time to seconds, not minutes. The logic was sound in missile defense scenarios, where delays could result in catastrophic ship loss. However, this same logic reduced the temporal bandwidth available for cross-checking civilian flight data, consulting external air traffic control sources, or reassessing initial assumptions. The system functioned like a high-gain amplifier. Small interpretive errors were rapidly magnified into decisive action. From the perspective of the Airbus crew, none of these stresses were apparent. The cockpit environment was stable, governed by standardized procedures and predictable system behavior. The pilots relied on their instruments and clearances, trusting that their transponder broadcasts and adherence to civilian protocols ensured visibility and recognition. This trust represented its own form of confidence architecture, one built on international norms rather than weaponized technology. As Flight 655 climbed through successive altitude blocks, its radar signature evolved in a manner consistent with a heavy transport aircraft. Its speed increased gradually, constrained by climb performance and air traffic restrictions. There were no abrupt accelerations, no aggressive maneuvers, no deviations from assigned heading. Yet within the Vincennes combat system, these parameters were abstracted into numerical trends that could be misinterpreted when divorced from civilian context. The invisible forces acting upon the situation were not aerodynamic or structural, but informational. Data latency, display scaling, and operator workload all exerted pressure on decision-making. When multiple tracks compete for attention, prioritization becomes critical. In such moments, the most salient cues, those aligning with perceived threat, tend to dominate. This is analogous to stress concentration in materials. Load is not evenly distributed, but focuses on specific points until failure initiates. The Vincennes radar operators reported a target believed to be descending and accelerating, consistent with an attacking military aircraft profile. Subsequent analyses would show discrepancies between recorded data and operator perception, highlighting how system displays and human interpretation diverged under stress. This divergence was not the result of negligence or incompetence, but of design assumptions that underestimated the impact of cognitive load in mixed-use airspace. Meanwhile, communication channels added another layer of complexity. Radio transmissions warning unidentified aircraft were broadcast on military distress frequencies, not on civilian air traffic control channels monitored by commercial pilots. From an engineering standpoint, this was a logical separation of domains. From an operational standpoint, it created an information gap. The Airbus crew never received warnings intended for them, reinforcing their assumption of safety. The environment thus became a closed loop of misaligned signals. The warship interpreted the absence of response as noncompliance. The aircraft, unaware of any challenge, continued its climb. Each system operated correctly within its own domain, yet the domains failed to intersect meaningfully. This is the essence of systemic stress. Components perform nominally, but interfaces fail under conditions they were never designed to handle. As time progressed, the stress intensified, the perceived threat window narrowed, and the opportunity for reevaluation diminished. The Vincennes combat team faced a decision space compressed by seconds, where hesitation was equated with vulnerability. In such a space, confidence in system output becomes a substitute for certainty. The architecture of confidence, initially a strength, now functioned as a structural load bearing down on judgment. From a forensic engineering perspective, this phase represents the accumulation of invisible forces that precede failure. Just as repeated aerodynamic loading can initiate microcracks long before visible damage appears, repeated cognitive stress can degrade decision-making integrity without obvious warning signs. By the time the system reached its critical point, reversal was no longer feasible. The tragedy of Iran Air 655 was thus set in motion not by a single erroneous input, but by an environment that amplified stress across multiple layers: technological, organizational, and psychological. The aircraft continued its ascent, the warship its vigilance, and the gap between their realities widened. In that gap, the seeds of catastrophic misinterpretation took root, waiting for the precise moment when accumulated stress would convert uncertainty into irreversible action. The transition from stress accumulation to irreversible failure occurred within a narrow temporal corridor measured in seconds. In complex systems engineering, catastrophic failure rarely presents as a singular rupture. Instead, it emerges when multiple subsystems align in a configuration that permits error to propagate without attenuation. This moment represents the point at which latent conditions convert into kinetic consequence. Inside the Combat Information Center, the radar track associated with the climbing Airbus was already cognitively reclassified. What had initially been an ambiguous contact was now treated as a hostile entity. This reclassification did not occur through a formal system flag or mechanical switch, but through human interpretation reinforced by system symbology. Once a track is mentally assigned to a threat category, subsequent data is filtered to confirm that assignment. This phenomenon mirrors confirmation bias, but from a systems perspective, it functions as a positive feedback loop with no damping mechanism. The radar data stream continued uninterrupted. The target's altitude increased steadily, consistent with a commercial climb profile. However, altitude information was displayed in discrete updates rather than continuous analog form. In high workload conditions, discrete numerical changes are more susceptible to misreading than trend-based visual cues. A momentary misinterpretation of an altitude decrement as descent, even if corrected milliseconds later in raw data, could persist cognitively once framed as evidence of attack geometry. Speed calculations introduced additional ambiguity. The system computed closing velocity based on relative motion vectors. A climbing aircraft departing from a coastal airport and moving away from the ship could still register a closing component depending on vector orientation and ship maneuvering. These vector relationships are mathematically correct, yet counterintuitive, particularly under time pressure. What the system presented as numerical truth required interpretive translation that exceeded the available cognitive bandwidth. Simultaneously, the IFF subsystem returned Mode 3 civilian responses. These responses were logged, but their association with the radar track depended on correct correlation logic and operator attention. In a system optimized for military threat discrimination, civilian identification lacked salience. It did not generate alarms or force reconsideration. It existed as passive data. This design choice reflected an assumption that civilian aircraft would not appear threatening within a combat zone, an assumption invalidated by the operational context. As the perceived threat window narrowed, the decision-making process shifted from analytical to procedural. Rules of engagement, designed to provide clarity under fire, now constrained flexibility. The system's architecture emphasized compliance with predefined criteria rather than holistic reassessment. In engineering terms, the system entered a brittle regime, highly responsive but intolerant of deviation. The launch sequence required multiple confirmations, each intended as a safeguard. However, safeguards that rely on the same informational substrate do not provide true redundancy. Each confirmation drew from the same radar picture, the same misinterpreted track, and the same cognitive framing. This is analogous to redundant structural members fabricated from the same flawed batch of material. Redundancy exists in form, but not in substance. When the command to engage was given, the missile system executed flawlessly. Target designation data was transferred to the fire control system, guidance parameters were computed, and launch rails energized. The missile's solid rocket motors ignited with predictable thrust curves, imparting rapid acceleration. Guidance systems locked onto the radar-reflected energy from the designated target, adjusting control surfaces to maintain intercept geometry. There was no hesitation, no ambiguity, no mechanical failure. From the missile's perspective, the Airbus was simply a radar reflector with defined kinematics. Proximity fuses were calibrated to detonate when reflected signal strength exceeded threshold parameters, optimized to maximize structural damage by dispersing high-velocity fragments across aerodynamic surfaces and load-bearing frames. These systems were engineered to defeat military aircraft with robust structures. Against a civilian transport, the outcome was inevitable. The moment of detonation imposed extreme external loads on the airframe. Fragmentation penetrated the fuselage skin, severing frames, stringers, and control rods. Aerodynamic loading instantaneously exceeded design limits as lift asymmetry developed. Structural integrity collapsed not because of internal weakness, but because the applied forces dwarfed certification envelopes. The aircraft disintegrated along predictable failure paths dictated by its construction, not by any pre-existing defect. Inside the cockpit, there was no warning. The event unfolded faster than human reaction time. Data recorders ceased functioning as power and structural continuity were lost. From a forensic standpoint, the absence of distress calls or evasive maneuvers confirmed that the crew had no situational awareness of the impending catastrophe. The system that failed them was external, invisible, and entirely beyond their influence. On the warship, sensor displays immediately reflected target breakup. Radar tracks fragmented, altitude data ceased to update coherently, and debris fields expanded. These signatures were consistent with a successful engagement. In the immediate aftermath, system feedback reinforced the perception of correct action. The architecture of confidence now validated itself through apparent success, further delaying recognition of error. This feedback loop is critical to understanding the failure. Systems designed to confirm success based on internal metrics cannot distinguish between correct and incorrect outcomes if both satisfy engagement criteria. The missiles destroyed the target as intended. The system's metrics were met. There was no built-in mechanism to flag moral or contextual inconsistency. From a purely technical standpoint, the engagement was flawless. Only later, when external information penetrated the closed system, did dissonance emerge. Reports of a missing civilian flight conflicted with the internal narrative of hostile neutralization. This conflict required retroactive reconciliation, a process far more complex than initial threat assessment. In engineering accident analysis, this is recognized as outcome bias, the tendency to judge decisions based on results rather than decision quality under uncertainty. The frame-by-frame reconstruction reveals that no single decision point offered a clear off-ramp. Each step was locally rational within the system's logic. The failure was emergent, arising from interactions between subsystems whose combined behavior was not fully anticipated by designers or operators. This is the hallmark of complex system accidents. Inevitability emerges only in hindsight. The missile's detonation marked the physical end of the aircraft, but the failure sequence extended backward in time through layers of design philosophy, interface choices, and operational doctrine. The system did not fail by breaking. It failed by working too well, executing its programmed logic without the capacity for contextual self-doubt. In the seconds following the engagement, silence replaced data. The absence of further radar returns closed the loop, freezing the system state. For the crew, the event transitioned from imminent threat to resolved action. For the passengers and crew of the Airbus, it was the abrupt termination of a routine flight. The asymmetry of experience underscores the fundamental disconnect between the two systems involved. This moment of failure, when reconstructed with forensic rigor, exposes a critical vulnerability in high-confidence technological architectures. When systems prioritize speed, integration, and automation without equivalent investment in ambiguity management, they become susceptible to catastrophic misclassification. The destruction of Iran Air 655 was not the result of chaos, but of order misapplied, of a system executing certainty in a world that demanded restraint. By the time the physical evidence began its descent into the waters below, the failure had already completed its full cycle. Nothing in the remaining seconds could alter the outcome. The catastrophe was sealed not at launch, but at the moment when accumulated stress, biased interpretation, and unchallenged system authority converged into action. The forensic phase began not with clarity, but with fragmentation, both literal and institutional. The physical wreckage of the aircraft descended into the Persian Gulf in a debris field consistent with mid-air disintegration, dispersing fuselage sections, wing components, and human remains across a wide maritime area. Unlike accidents governed by material fatigue or progressive structural failure, the pattern here exhibited signatures of external high-energy fragmentation. Penetration holes with inward bent edges, localized spall damage, and severed structural members indicated an explosive event occurring outside the pressure vessel, imposing asymmetric loads that exceeded ultimate strength thresholds instantaneously. Naval recovery operations retrieved debris under conditions constrained by depth, currents, and political sensitivity. From a forensic engineering standpoint, the most critical evidence was not the complete airframe, but representative samples, fuselage skin panels, wing spars, and avionics fragments exhibiting high-velocity impact signatures. Metallurgical examination revealed clean perforations consistent with preformed missile fragments traveling at supersonic velocities. There were no signs of fatigue striations, corrosion pitting, or pre-existing cracks. The aircraft's structural integrity prior to impact was intact. Attention quickly shifted from airframe analysis to system causality. Unlike conventional aviation accidents, where the focus centers on mechanical degradation or pilot error, this investigation was dominated by command and control analysis. The United States Navy initiated an internal investigation, while external scrutiny came from international aviation authorities and civil organizations. The absence of jurisdiction by civilian investigative bodies underscored a fundamental asymmetry. The aircraft was civilian, but the causal system was military. Data reconstruction relied heavily on shipboard records. The Aegis Combat System generated time-stamped logs capturing radar tracks, operator inputs, and system status. These logs formed the backbone of the forensic timeline. Analysts reconstructed the sequence of events down to the second, correlating radar data with recorded IFF interrogations and engagement decisions. The data showed that the radar track associated with the Airbus was continuously present, its altitude increasing monotonically. No recorded data supported a descending profile consistent with an attack run. This discrepancy between recorded data and operator perception became a central forensic finding. Human-machine interface analysis revealed that altitude and speed information were displayed in formats vulnerable to misinterpretation under stress. Numerical readouts lack persistent trend visualization, forcing operators to mentally integrate successive values. In high-workload environments, such integration is prone to error. This was not a failure of the radar's measurement accuracy, but of the interface's cognitive ergonomics. IFF analysis further complicated the narrative. Logs confirmed that Mode 3 civilian transponder responses were received. However, correlation between IFF responses and radar tracks was not enforced by the system. Operators were required to manually associate the data streams. In a system optimized for military engagement, civilian identification did not override threat classification. The forensic conclusion was unambiguous. The system permitted, and implicitly enabled, the engagement of a target broadcasting a valid civilian code. Laboratory simulation played a critical role in validating these findings. Using recorded data, investigators reconstructed the engagement scenario in controlled environments, replicating display configurations and operator workloads. These simulations demonstrated how a combination of ship maneuvering, relative vector geometry, and display scaling could create the illusion of a descending, accelerating target despite contrary raw data. The system did not generate false data. It generated data that required correct interpretation under time pressure, a requirement that exceeded realistic human performance margins. Parallel to technical analysis was the examination of organizational factors. Rules of engagement were scrutinized for ambiguity and bias. Investigators noted that the criteria for hostile intent relied heavily on kinematic profiles derived from military threat libraries. These libraries were not calibrated for civilian climb profiles originating from nearby airports. The assumption that a threatening aircraft would originate from a distant airbase rather than a civilian terminal was implicit, not explicit, leaving room for catastrophic misclassification. Communication analysis exposed further systemic weaknesses. Radio transcripts confirmed that warnings were transmitted exclusively on military frequencies. Civilian air traffic control channels, monitored by the Airbus crew, were not used. This procedural separation reflected doctrinal silos rather than technical necessity. From a systems engineering perspective, this represented a failed interface between two safety-critical domains. The absence of cross-domain communication removed a potential barrier that could have interrupted the failure sequence. One of the most revealing aspects of the forensic process was the absence of traditional smoking gun failures. There was no defective component to replace, no cracked weld to redesign, no software bug to patch in isolation. Instead, investigators confronted an emergent failure arising from the interaction of correct components. The radar worked as designed. The missiles functioned nominally. The operators followed established procedures. Yet the outcome was catastrophic. This forced a reframing of causality. The investigation concluded that the root cause was not an isolated error, but a systemic mismatch between system design assumptions and operational reality. Aegis was engineered for high-intensity naval combat, not for discrimination in congested civilian airspace. Its success metrics were binary, engage or not engage, without gradation for uncertainty. In such a framework, doubt is treated as risk rather than information. International reaction intensified scrutiny. Civil aviation authorities emphasized that the aircraft had complied fully with all civilian regulations. Flight plans were filed, transponders active, communication procedures followed. There was no deviation, no anomaly. This placed the burden of explanation squarely on the military system. The absence of an independent civilian investigative authority with full access to military data limited transparency, further eroding confidence in the findings among the international community. From a forensic philosophy standpoint, the investigation highlighted a critical limitation in accident analysis when military systems are involved. Traditional frameworks, such as those employed by the National Transportation Safety Board, emphasize mechanical causation, human factors, and organizational oversight. In this case, jurisdictional boundaries prevented full application of these methodologies, leaving systemic insights fragmented across reports and statements rather than consolidated into a single authoritative narrative. Despite these constraints, several technical conclusions were unavoidable. The engagement was based on misinterpretation of sensor data, exacerbated by interface design and cognitive load. The system lacked effective safeguards against confirmation bias. Redundancy existed in hardware, but not in interpretation pathways. There was no independent verification channel capable of halting the engagement once the threat narrative crystallized. The forensic aftermath thus extended beyond debris analysis into the realm of systems ethics. Engineers and analysts were forced to confront the uncomfortable reality that high-reliability systems can fail catastrophically without violating any internal rules. This realization challenged the prevailing belief that automation and integration inherently improve safety. In environments characterized by ambiguity rather than clear adversarial signals, these same attributes can amplify risk. By the conclusion of the investigative phase, the physical evidence had been cataloged, the data reconstructed, and the procedural failures documented. Yet the most consequential finding was abstract. That confidence itself can become a failure mode. When systems are designed to minimize doubt, they also minimize opportunities for correction. In this sense, the wreckage of Iran Air 655 was not only scattered across the Gulf, but embedded within the assumptions of modern combat system design. The forensic record closed with no modifications to the destroyed aircraft, because none were warranted. The Airbus A300 did not fail. The failure resided entirely within the system that classified it. This distinction is crucial. It reframes the tragedy not as an aviation accident in the traditional sense, but as a systems accident, one in which the boundary between civilian safety and military defense proved catastrophically permeable. As the investigation receded into reports and classified annexes, its implications remained unresolved. The evidence pointed not toward individual culpability, but toward architectural responsibility. The question left unanswered was whether future systems would absorb this lesson, or whether confidence, once again, would be allowed to masquerade as certainty. The legacy of Iran Air 655 did not materialize as a single corrective action or a clearly defined redesign. Instead, it propagated slowly through doctrine, interface philosophy, and the uneasy relationship between civilian aviation safety and military command systems. Unlike failures driven by material fatigue or structural overload, this event resisted closure because it exposed a deficit not in hardware, but in epistemology, how complex systems claim to know what they know. In the immediate aftermath, official responses focused on procedural clarification rather than technological reform. Rules of engagement were reviewed, wording adjusted to emphasize positive identification, and training curricula updated to stress caution in mixed-use airspace. These measures addressed surface-level contributors but left the deeper architectural assumptions largely intact. The Aegis Combat System remained fundamentally unchanged in its core logic. It continued to prioritize rapid threat resolution over uncertainty management. The belief that speed equated to survivability persisted, reinforced by decades of missile defense doctrine. Yet within engineering and human factors communities, the incident triggered a more profound reassessment. Analysts began to recognize that high-integration systems exhibit a form of brittleness when confronted with ambiguity. Redundancy in sensors and processors does not equate to redundancy in interpretation. When multiple data streams are fused into a single authoritative display, dissenting information is often suppressed rather than highlighted. This design choice simplifies action but undermines resilience. One of the most significant, albeit subtle, shifts occurred in interface design philosophy. Subsequent generations of combat and air traffic management systems began to incorporate explicit uncertainty indicators. Rather than presenting classifications as binary states, designers explored probabilistic representations, confidence intervals, and trend visualizations. These features acknowledge that sensor data is inherently incomplete and that forcing certainty can be more dangerous than admitting doubt. While such changes were incremental, they marked a departure from the absolutism that characterized earlier systems. Civil-military coordination also emerged as a focal point. The separation between military distress frequencies and civilian air traffic control channels was reevaluated. In several regions, protocols were revised to encourage cross-domain communication when military operations occurred near civilian airways. This did not eliminate risk, but it introduced additional barriers against misclassification. From a systems engineering perspective, these barriers functioned as energy absorbers, dissipating error propagation before it could reach catastrophic levels. The incident further influenced international discourse on the responsibility of military operators in civilian airspace. Aviation safety culture, long shaped by the principles of just culture and non-punitive reporting, struggled to reconcile with military command structures rooted in obedience and rapid execution. The philosophical tension between these cultures became evident. Civil aviation treats deviation as information, military systems often treat it as threat. Bridging this divide required not only procedural alignment, but cultural recalibration. Technologically, advances in sensor fusion and artificial intelligence promised improved discrimination capabilities. Machine learning algorithms were proposed as solutions capable of recognizing nuanced flight profiles and distinguishing civilian patterns from military ones with greater accuracy. However, the lessons of Iran Air 655 cast a long shadow over such optimism. Automation that merely accelerates classification without embedding ethical or contextual reasoning risks replicating the same failure at higher speed. Engineers increasingly acknowledge that algorithmic confidence could amplify error just as effectively as human certainty. From a philosophical standpoint, the event underscored the concept of normal accidents in tightly coupled systems. When processes are interdependent and time-compressed, small errors can cascade uncontrollably. The Vincennes engagement exemplified this dynamic. Once the system entered its engagement pathway, there was no graceful degradation mode, no mechanism to pause and reassess. The system's success depended on uninterrupted execution, and interruption itself was treated as failure. This realization influenced safety analysis methodologies beyond military applications. In civilian aviation, it reinforced skepticism toward excessive automation without transparent human oversight. Designers revisited assumptions about pilot authority, emphasizing the importance of maintaining meaningful human control rather than relegating operators to passive monitors. The parallels were clear. Whether in a cockpit or a combat information center, humans must remain active interpreters, not mere executors of machine logic. The moral dimension of the legacy cannot be ignored. The destruction of a civilian aircraft by a state actor using advanced technology challenged prevailing narratives about precision warfare. Precision, it became evident, is not solely a function of weapon accuracy, but of target understanding. A missile can strike exactly where it is guided and still represent a profound failure if the guidance premise is flawed. This distinction reshaped discussions about accountability in technologically mediated violence. In policy circles, the incident contributed to broader debates about transparency and trust. The reluctance to submit the event to an independent civilian investigative body limited the perceived legitimacy of official conclusions. This highlighted a systemic gap. When military systems cause civilian harm, existing investigative frameworks are ill-equipped to provide comprehensive, trusted analysis. The absence of such mechanisms perpetuates suspicion and hinders learning. Over time, the legacy diffused into training manuals, design reviews, and academic literature. It became a case study not of negligence, but of overconfidence. Engineers cited it when arguing for humility in system design, emphasizing that no amount of redundancy can compensate for flawed assumptions. Human factors specialists used it to illustrate how stress, expectation, and interface design interact to shape perception. Strategists referenced it as a cautionary tale about operating advanced weapons in complex environments. Yet the most enduring legacy lies in its unresolved tension. Despite incremental reforms, the fundamental challenge remains: how to design systems that act decisively without becoming dangerously certain. The temptation to equate automation with objectivity persists, especially as computational power increases. Iran Air 655 stands as evidence that objectivity is not guaranteed by electronics. Data must still be interpreted, and interpretation is inseparable from human context. In the final analysis, the event reshaped aviation not through sweeping redesigns, but through a gradual erosion of naivete. It forced acknowledgement that progress carries hidden costs when complexity outpaces comprehension. The passengers and crew of Flight 655 became unwilling participants in an experiment that revealed the limits of technological confidence. Their loss exposed a vulnerability that had always existed, concealed beneath layers of capability and doctrine. The philosophical lesson is stark. Systems built to eliminate doubt may succeed operationally, but they fail ethically when doubt is warranted. Safety, whether in aviation or warfare, depends not on the absence of uncertainty, but on the capacity to live with it responsibly. The cost of ignoring this principle is measured not in damaged hardware, but in irrevocable human loss. As modern systems continue to integrate sensors, algorithms, and autonomous decision-making, the legacy of Iran Air 655 remains relevant. It warns that the future's most dangerous failures will not announce themselves through broken parts or alarm bells. They will emerge quietly, when systems perform exactly as intended, and certainty goes unchallenged. In that sense, the true wreckage of Flight 655 is not confined to the seabed of the Persian Gulf. It endures wherever confidence is allowed to override caution, and where technology is trusted more than understanding.